Integration by parts is an integration formula, and it's just a way of kind of working backwards from the product rule for derivative. Now, we don't really use the word formula or rule for these because it won't always work. There's a specific kind of integral that it's going to work with, and sometimes even if you can use it, it can be tricky and take a little bit of strategy. So I'm going to show you where the integration by parts formula comes from. If this were a normal world, I would make you memorize it, but I can't, so just bear with me. There's the product rule. The derivative of a product of two functions is f prime times g plus f times g prime. And we're just going to manipulate that and move it around a bit. So I'm going to rewrite that as in, rather than the derivative of the left side is the right side, the integral of the right side is the left side. So if you had the integral of f prime times g plus f times g prime, that would just be f times g. So that's literally just the product rule written backwards. Now I'm going to move that around a bit. So I'm going to split up that left-hand side into two integrals. I can do that. That's just splitting an integral up into two things. So now what I want is I want that second integral by itself. I want the integral of f times g prime by itself. So I'm just going to subtract that first integral off of both sides. And here's what I end up with. The integral of f times g prime equals f times g minus the integral of f prime times g. That's the integration by parts formula, but that's not how you're going to see it. There's a simpler way to see it where we rewrite it using kind of differentials instead of function notation that makes it easier to memorize and just easier to see. We're going to let f of x equal u and g of x equal v. So that way, that like g prime of x dx, like you see in that first thing, is just dv. And f prime of x dx, like you see in that last thing, is just du. So it makes everything look simpler to rewrite it in terms of differentials. Remember, if u is a function of x, the definition of du, the differential of u, is f prime of x times dx, which again has no quantity. It's just equal to 1. So that's how you'll see it. The integral of u times dv equals uv minus integral of v du. I guess if I'm using this in the future, and this isn't an in-person class, you have to memorize this formula. So what this says is, okay, the integral of a function times the derivative of some other function is those two functions minus the integral of the second function times the derivative of the first function, which in theory it looks like what? You'll see how it works in practice right now. That's just the formula repeated. So here's a classic integration by parts, just x times e to the x. So you look at this and you'd say, okay, well, I can't do your substitution here because my inner function, my x, doesn't really give me a derivative. So it looks like we did the integral of x times e to the x squared before, and we did that by substitution. So it's a fine little difference between this and that, but it's a totally different technique to do it. So you just kind of have to build up your repertoire and recognize like, oh, I can use parts here, I can use substitution here. So the main thing right now with integration by parts, the first thing you always have to do is pick which one of these is your u and which one of these is your dv. You're going to take your u and differentiate it because you need a du. You're going to take your dv and integrate it because you need a v. So we have two functions here, x and e to the x. We can differentiate and integrate both of those, no problem. But the general rule is you want to differentiate the one that gets simpler. So if u were e to the x, my du, see there's a du in that formula, would still be e to the x. So that doesn't seem simpler. If I pick my u to be x, the derivative of x is just 1. So that du would essentially go away. So usually if it's x times a function, you're going to pick x to be your u, but not always. That's why it's a technique, not a rule. Okay, so my u is going to be x, and my dv is going to be e to the x dx. So whatever our dv is, you have to be able to integrate it. We'll see that in the next example. There's certain stuff we don't know how to integrate, so that just can't be dv. So once you've picked that, then you're going to go ahead right now and do du and then do v. So you're always differentiating one thing and integrating the other thing. I say du is 1 dx. I didn't have to put that 1 there, but the derivative of x is just 1. So you won't see it in the next step. And then dv is e to the x dx. What is v? Well, v is just e to the x. So I did integrate there. This might be kind of a weird example. The integral of e to the x is e to the x. I did integrate that, okay? Putting everything into the integration by parts formula, the integral of, okay, u times dv is x e to the x dx equals u times v. So just look at your little chart there and you go u times v minus the integral of v times du. And see, we've made that integral of v times du doable now. Now it's just the integral of e to the x dx, right? So you're still going to always have to do another integral in this. It's just the idea is to make it doable. So the integral of e to the x is just e to the x, and what you get is x e to the x minus e to the x plus c. There's no reason to put a plus c in the original formula. Just stick it in at the very end. Again, I'm encouraging you to check these by differentiating. It doesn't really look like that the derivative of that is x e to the x, but just think about it. If you were to differentiate your result there, the derivative of x e to the x is, okay, x times e to the x plus 1 times e to the x. So what you get with the whole thing is x times e to the x plus e to the x minus e to the x, right? So what it does is the product rule cancels something out and you're left with just your original function. So in the meantime, you know, some of these look like too complicated, like they're not right. So check them. It's about to get more complicated here. Okay, so like I said last time, the conventional wisdom is to pick whichever one of these two functions gets simpler when you differentiate it, pick that to be your u. But let's think about it. If I pick my u to be x squared, the derivative of that is 2x. That is simpler, right? The power went down by 1. However, if I did that, I would have to pick my dv to be natural log of x, which would mean I would have to know an integral for natural log of x, which we don't. I mean, I do, but we don't yet in the class. We actually will get that today. So that right there is just like process of elimination. You can't do it that way. So think about it though. If you pick your u to be ln of x, well, the derivative of ln of x is just 1 over x. So that actually did get kind of simpler too, right? There's no ln in there. So it's not always the x or the power of x that you pick. The only other thing you might really pick is a natural log, although there are certainly variations. So you see what I mean? Different ones of these can be different. But by the fact that we don't have an integral for ln, we have no choice. We have to pick u equals ln of x, and then our dv is x squared dx. Right? So sometimes you have a choice. Here, no choice. Okay, now remember we're differentiating one and integrating the other. Du is 1 over x dx, and then v. So now you can see more clearly than the last example, I integrated. Whatever you pick for your dv, you're going to end up integrating. So that got more complicated, but there was no other way to do it. So that being said, stick everything into the formula. Okay, so u dv minus the integral of v du. So again, just look at your chart and kind of just go across. So it's uv minus the integral of v du. So it's natural log of x times x cubed over 3 minus x cubed over 3 times 1 over x dx. So that first chunk is taken care of. If you look at that second chunk, it's about to simplify. Right, so in this case, we got an integral that we know how to do because, well, there's just a 1/3 in it, and then an x cancels out. Okay, so I combined that first term into just one thing and made it look nicer. X cubed times ln of x over 3 minus 1/3 the integral of x squared, which, hey, we know how to do that. So the integral of x squared is just x cubed over 3. So I guess I kind of did a step in my head there where I said, okay, 1/3 times x cubed over 3 is x cubed over 9. Hopefully that's okay. So the final result is x cubed times ln of x over 3 minus x cubed over 9 plus a constant. So, right? Weird. You would not have guessed that that's the derivative of that thing is just x squared ln of x. So to check this one by differentiating would take a little work because you have these constants and then you'd have to use the product rule on the first term. But you could do it, and I would encourage you to do it. Take the derivative of that thing we just got, clean it up. You'll see a bunch of cool cancellation happens, and all you're left over with is x squared times ln of x. Okay, as promised, we can find an integral for ln of x using integration by parts. And I know it doesn't look like it. This doesn't look like the two examples we just did. The examples we've done so far are products of two functions. There's only one thing here. So what the hell? Do it anyways. Okay, so the nice thing though is, okay, well, so there's an ln of x and a dx. If we pick our dv to be ln of x, that's the same thing as last time. We don't know the integral of that. That's what we're trying to figure out. That's some circular logic. So boom, we have no choice. So if it's just a singular function like this, we have to let u equal ln of x, and then dv is just dx. So you could say dv is just 1, right? Our other function here is just the quantity 1. So that's what we do. U is ln of x and dv is just dx. You could, again, think about it as 1 dx. So du is going to be 1 over x dx, just like it was last time. And then v is just, okay, the integral of dx, so the integral of 1, which is just x. Right? Think about that going the other way. The differential of x is, by definition, just dx. It's just the derivative of x, which is 1 times dx. So when you go the other way, you just have an x. Okay? Now plug and chug. So it's going to be uv, right, minus the integral of v du. So that's ln of x times x minus the integral of x times 1 over x. And hey, would you look at that? X times 1 over x is just 1. How about that? So I just rewrote that as x ln of x minus the integral of just dx. So when you see the integral of just dx, just imagine there's a 1 there. Right? If there wasn't, it wouldn't do anything. But don't. That's a little more clear to see that the integral of just dx by itself is x. There you go. Now we have one. Yay, we have an integral for the natural log function. It's x ln of x minus x plus c. So again, just think going backwards. If you did the product rule on that first term, you would get something that canceled out, and all you'd be left with is the natural log. It works. So throw that one in your table of integrals. That was the only like basic function that we didn't have an integral for yet. So hooray, now we do. One more just straightforward example. So the integral of x cubed e to the x. So this looks a lot like the first one. It's just got an x cubed in it. So if we picked our u to be e to the x, you just keep getting like our du would be e to the x. So nothing would really change. Not only that, but our dv would have to be x cubed, which means we'd have to integrate that and we get x to the 4th over 4. So now the power is going up, and we don't really like that. We want the power to go down. So this is just like the first one in that, okay, we have to pick u equals x cubed, and dv is e to the x dx. Du is 3x squared dx, and when we integrate, v is e to the x. So we did integrate there. Putting that into our formula, we have uv, so x cubed times e to the x, minus the integral of v du, so that's e to the x times 3x squared. So I just took the 3 out front. So here's what we got. X cubed e to the x minus 3 times the integral of x squared e to the x. Okay, well, that second integral there now isn't like eminently doable. Like we can't just do it right away. But I mean, just look at it for a second. What technique do we know that we can use to do that second integral? Why? It's integration by parts. So there's nothing that says you can't just use it again. All right, so you just got to keep going and do it again. Now I'm going to keep using the variables u and v because I don't think it's that confusing, but if you want to switch to s and t or something, maybe I would just keep it like this. So we got the first part, now we're just working with the second integral. We're going to use exactly the same move. We're going to say, okay, u has to be x squared and dv has to be e to the x, because when you differentiate x squared, it does get a little bit simpler. So our du is 2x dx and our v is then just e to the x. So really, same kind of thing again. Now I'm going to kind of ignore the first part and just work with the integral of x squared e to the x, and then we'll put everything back together at the end. I don't want to keep copying everything every time. Okay, so the integral of x squared e to the x is x squared e to the x minus 2 times the integral of x e to the x. So we've still got an integral in our thing, but look at it. It's the first example I did, isn't it? Right? So let's not do it again. I already did the integral of e to the x. It was the first example we did today. So we'll say that one's in the book now. That one's in the big book of integrals, and we don't have to do it anymore. So just look back and figure out what it was. I'm not using the plus c because there's no reason to stick that on until the very end. So we already figured out that the integral of x e to the x equals x e to the x minus e to the x. And now I'm going to put everything back together. So that whole thing I just got, is going to go in the expression for the integral of x squared e to the x, and that whole thing I just got is going to go in the expression for x cubed e to the x. I don't know if this way is easier to you. It's easier to me. Okay, so the integral of x cubed e to the x is x cubed e to the x minus 3 times that second integral, which was x squared e to the x minus 2 times that third integral, which was x e to the x minus e to the x. So we've got some nesting going on here. Again, to me, that's easiest just to put it all back together at the end. You could leave it like that, but I wouldn't. We want like a good solid integral for x cubed e to the x. Because again, if you see it again in the homework or whatever, you know, now you can just use it. And there's obviously whole tables full of integrals you can get out there. So let's just clean that up as much as we can. Get rid of that first set of parentheses by just distributing the minus 2, and then just get rid of that next set of parentheses. And that's what it is. So if you look up the integral for x cubed e to the x, that's what you're going to find. It's x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x. Checking that by differentiating, oh boy, you could, but you'd have to do the product rule a bunch of times and it would be a pain. So this might be one that you just want to take my word for it. Or again, just type x cubed e to the x into like Wolfram Alpha and it'll show you the integral. I know you know what that is. And then you'll see that we're right. So that's where that came from. Now you know. The production from a machine used to mine coal is a continuous income stream with a rate of flow at time t given by this. F of t equals 28,000 minus 280,000 minus 14,000 t dollars per year. So it's a continuous income stream that is going down at a constant rate, right? This is a linear function, which you would expect. These things do go down over time. So if the money is worth 7%, so we're investing it at 7% compounded continuously, find the present value of this machine, right? Given that we're going to be investing the income from it at 7% continuous interest over the next 8 years. So this is just a formula for present value. Glance back and see what that is. It had a e to the negative rt in it. And obviously it's going to go into an integral. And there it is. So it's for the next 8 years. That's our f of t, our flow function, times e to the negative rt. So remember, r is not 7, r is 0.07. dt. Okay, so this one is going to be kind of a beast, so get comfortable. Not that the integration is that hard, but the numbers are going to be real ugly. But that's kind of, that's how it is. And I'll tell you how to check it at the end, but no cheating. Okay, so one could split this up into two integrals, like distribute those parentheses and say, okay, it's 280,000 times e to the whatever minus 14,000 t times e to the whatever. I think the way I'm about to do it is faster, because one of those integrals would be fairly straightforward and the other one would be an integral by parts, obviously. So it's easier just, I think, to just do it all by parts right now. So I'm going to let my u be 280,000 minus 14,000 t, and my dv be that e thing, because the derivative of that first thing is just going to be negative 14,000, which is just a constant. So that will make my subsequent integral simpler. Like that. Now, could you do it the other way? Yes, I think it's more work. It's not easy either way. Okay, so du is going to be just negative 14,000 dt, right? And then v, so we have to integrate e to the negative 0.07 t, and I think we've done this enough that we know that all that's going to happen is there's going to be a 1 over negative 0.07 in there. So if that doesn't make sense, just think about the derivative of v. The negative 0.07 would come out and cancel that first thing. So we're just doing that backwards when we apply that rule. Okay, so that's our u, our v, and our du that we need. So throw that all into the integration by parts formula. It's not pretty. So uv is 280,000 minus 14,000 t times v, which is negative 1 over 0.07 times e to the negative 0.07 t, and then minus v du, which is negative 1 over 0.07 e to the negative 0.07 t times negative 14,000 dt. Again, if you're feeling bold and you want to just pause the video now and go ahead and see if we get the same number, great. This isn't anything we haven't done before. It's just you got to be real careful because these are ugly numbers. So let's see. To clean up that integral, I've got a triple negative going on right now, right? So the thing inside the integrand is a minus times a minus, so let's just make that a plus, and then it's still going to be minus that integral. The other thing is that this is a definite integral, so at the end we are going to evaluate it from 8 to 0, but what I would do is just ignore that for now and just work on getting an indefinite integral for that original thing, and then at the very end, at the very last step, we're going to plug in that 8 and that 0, and it's going to involve a lot of just calculator work. Okay, so I did two things there. I got rid of the double negative inside the integrand, and then and then I moved the 14,000 and the 0.07 to the outside because those are just constants and they're not going to do anything. So now the only thing inside of our integral, the only thing we have left to integrate is e to the negative 0.07 t, which we know is going to be e to the negative 0.07 t, and then it's going to have a 1 over negative 0.07. So it's going to have another one of those. Okay, so I didn't mess with the first part, so now I've got minus 14,000 over 0.07 times negative 1 over 0.07 e to the negative 0.07 t. Again, this is the easy way. Let's just clean up that second term a little bit. That becomes a plus. 0.07 times 0.07 is 0.0049. And that's it. I mean, we can distribute those first parentheses, but I don't know that we're going to get it much better than that. So that's the thing. We're not done. We have to evaluate that from 8 to 0. Like that. So now we just start plugging and chugging. If you're really confident with your calculator moves, or if you're using some other kind of software to do this, then maybe you can jump right to the answer from right here. Up to you. I'm going to plug in some numbers just so you kind of see what I even did. Okay, 280,000 minus 14,000 times 8, so that's the upper bound, times negative 1 over 0.07 times e to the negative 0.07 times 8, plus 14,000 over 0.0049 times e to the negative 0.07 times 8, and then minus, you have to do brackets here, right? It's minus all of that stuff evaluated as 0. Unfortunately, it's not just all 0. So it's minus brackets 280,000 times 0 times negative 1 over 0.07 times e to the 0. E to the 0 is 1. Plus 14,000 over 0.0049 times e to the 0. I'm going to clean that up one step further before I punch it in. So let's see, 280,000 minus 14,000 times 8 is 168,000. And then it's times 1 over 0.07, e to the 0.07 times 8 is 0.56. And then it's plus another 14,000 over 0.0049, e to the negative 0.56, minus, okay, there's that 0 goes away, so it's 280,000 times negative 1 over 0.07, e to the 0 is just 1, so that goes away, plus 14,000 over 0.0049, again, the e to the 0 goes away. Woo! Okay, I don't think there's any reason to go further than that. I think you should be able to mash this all on your calculator. Just be really careful, obviously, with parentheses and negative signs, and probably double check it. So whatever number you get, well, here's the number I got. You can check that if you, so there's two ways. In your TI calculator, you graph the original thing. Graph 280,000 minus 14,000 t times e to the negative 0.07 t, whatever that looks like. And then go to calc, which is up here by trace. And let's see if you can even see it on the screen. There's a little integral symbol. Yep, can you kind of see it? Okay. It says, yep, there it is. Integral of f of x dx. It's going to take you to that function, and it's going to take you to the graph, and it's going to ask you for the lower limit and the upper limit, and then it'll calculate it. The other way to do it that might be even faster is to go to the website wolframalpha.com. I'm not going to put that on the screen because you already know where it is. So Wolfram Alpha. And you can literally just type in the function and then type like integral from 0 to 8. So again, you can't just do that. But with these ones, the numerically are gnarly, right? It would be super easy to make a little arithmetic mistake in here. Anyone would do it. I would do it. So these ones that are numerically nasty, there's nothing. That's really the only way to check it. It's not like you're going to go through all those steps again. Yuck. So use your technology to check it, but you should be able to do that. So that's an applied integration by parts.